Alright guys, welcome back um, to the deep learning tutorial series. We shall continue from where we last stopped. We were talking about activation functions. We look at the sigmoid. Now we're looking at another type of activation function, which is the hyperbolic tangent. Essentially, the only difference between the sigmoid and the hyperbolic tangent or tan h is that all the output of tan h they fall between -1 and 1, unlike the sigmoid, which is between 0 and 1. And this is the formula that gives us the hyperbolic tangent. So if you look at this formula and you key in the x values, say -10 or 10 or 0, you discover that you get this shape for the tan h. So you will see here that this curve passes through the center of 0. At the center it passes through 0. So when x is 0, the value of the activation function is also 0. That is why we say that tan hx is 0 centered, and this is an advantage. But also, there's still the problem of saturated neurons when we have all the values in this, when all the values are 1 and when all the values are -1. When all the outputs are -1, it means that when x is sufficiently large enough, whether to the positive side or to the negative side, the neurons saturate. They don't change. Another important activation function, which is frequently used, is the ReLU, the rectified linear unit. And the ReLU function just simply says, no matter the value of your x, it returns the value unless the x is less than 0. So when the x is less than 0, then it returns 0. As you can see here, if x is -10, the value will be 0 to the y-axis. When x is less than 0, the value is 0. When x is 0, is 0. But when x is positive, then the value will just be the same. You can trace it to the y-axis. The value will just be the same value with the value of x. So because of this, the value which was invented by Krzyzewski et al. In 2012 has the following advantage. Number one is it does not saturate, at least in the positive region. You can see that here this continues to increase. It doesn't saturate. If your x is 1 million, you also have 1 million. If your x is 50, you also have 50. So this doesn't saturate in the positive region. But you can see in the negative region, it does saturate. That's a disadvantage. So as the number increases on the negative, the values does not change. It's just we can't learn anything. It's just 0, just return zeros. And we don't want saturated neuron when you're doing back propagation. It's computationally efficient, just take the max or you put 0, and it converges much faster in practice. So we also have dead ReLU neurons. So let's look at the ReLU in the area of the negative region. What it means that it saturates. Now, if we have this computational unit, which is using a ReLU function, and this we are using this sigmoid to represent our value. Now when you're doing your error back propagation, L is the loss, and you are differentiating the loss with respect to the output of the value. So you have the L, the sigmoid. So to be able to do that, you differentiate, to be able to get this, to differentiate the partial derivative of our loss with respect to x, which is actually this is supposed to even be w. This is our weight. So when you're trying to differentiate that, so to get that, to get your dl, the x, you do from dl, the sigmoid, to the sigmoid, the x. That is, you're coming from here. So in order to be able to get dl, the x. So by now you are doing the partial derivative of L with respect to the output of the value. So here, when x is equal to 10, then we are able to get a value. So when x is 10, you can do the partial derivative of the sigma, because this will also be 10, 10. Okay? When x is 0, that is not differentiable because you're going to get a 0. You can't differentiate with respect to 0. And when x is minus 10, you are going to have everything to be, the result of your differentiation to be equal to 0. That's the saturation. So the value is active in the positive region, and dead value will never activate, to never update. The main reason for dead value neurons is when you have unlikely weight initialization, or you have a high learning rate. Another example of the activation function is the leaky value. So the leaky value is just a slight multiplication of value, which just multiply the values of x in the negative region with a constant value. This eliminates the problem of saturating negative region. So this does not saturate at all, whether in the positive or negative region. You see that you always continually have different values as this can continue. It is 0 mean, you see here, it's passing through the 0. It's computationally efficient too. It converges much faster, and it doesn't die because it doesn't have saturation. So it's a great improvement over the value. So we also have the parametric rectifier p value, where you learn the alpha instead of just picking a constant 0.01. You can learn that value too. So this will be a learnable parameter. And these are proposed by Mas et al. And Hill et al. In 2015. You also have the exponential linear unit. These are just variations. So you introduce like exponential here whenever x is in the negative region. So it takes all the benefit of value, and it's also 0 mean, but it's a bit computationally intensive because you are using exponential, and negative saturation rate compared with Dkey, it may add some reversal. So you see here that by the time you put in values here, it seems as if it's like saturating in the negative region. Another example of the activation function is Maxout, and it uses this formula. You take the x, you multiply it by the weight 1 transpose plus the bias, then again there will be 2 transpose plus the second bias. So it does not have the basic form of the dot product, non-linearity. The positives, it generalizes ReLU and leaky ReLU. Linear regime does not saturate, does not die, but it doubles the number of parameters. That is the disadvantage. So the practical advice when you are trying to choose an activation function for your neural network design, use ReLU as the default. Don't use sigmoid at all. Be careful with your learning rate. You may want to experiment with few learning rate and see what works with the problem. You can try out Dkey, ReLU, Maxout, and Edu. You can also try out tanh, but in practice it doesn't give much. So that's all for this segment of looking at the activation function. We just quickly walk through the same thing from other resources that we have seen here. We have explained this. So sigmoid, we've looked at sigmoid before, but something to add is how the sigmoid behaves when you do the derivative. And you know, essentially, because you are doing error backpropagation, we need to do the derivative. So this is how sigmoid in green, that's how the behavior will be. The tanh, we mentioned it, and the second derivative of tanh, you see how it behaves when we do the derivative. Apology, not secondary. When we do the derivative, this is the way it behaves in green, and this is for ReLU. See, when we do the derivative of ReLU, this is how it is. So when you do the derivative, you see that on the positive side, you see when we differentiate, this is how it is when we do that. Then some important things here also. It's just comparing sigmoid and ReLU, and just what has been mentioned before. We mentioned leaky ReLU, that is when you have a parameter is always between a 0 and 1. Parametric ReLU, we're talking about learning the parameter, which we mentioned before. You also have the HeLU, which we also mentioned before, is a bit complicated because of this, because you have to use the exponential. And you can see derivatives. We also have some other ones like scaled exponential linear unit. That's just what this, it gives back x and is greater than or equal to, the only difference is in here, and you have additional training parameter, the lambda. That's about all that we have there for additional information on the different activation functions. The same thing here too. We can quickly look at this. We have seen the different activation functions, the sigmoid, the tanh. This even mentioned add tanh, and we are seeing linear here. I think I should suppose linear just means you are not using any activation function. Then you have the soft plus. We talk about the ReLU. You see it here again. Give you x whenever it is not negative. Talk about the leaky ReLU, which uses 0.01 to multiply x in the negative region. And that's essentially all. Thank you for listening. Kindly Drop your comment below on what you feel about activation functions and what are your experience with different activation functions. Thank you for listening. See you in the next one.